Welcome to week 2. We're going to be talking about particles of matter this week. So let's learn about atoms and their structure. In ancient Greece, philosophers thought matter was a combination of 4 elements: air, water, fire, and earth. We learned this last week when we spoke about Aristotle. Then Democritus came along, and he proposed that the world was made of empty space and tiny particles called atoms. So Democritus is the first to determine what an atom is and to define what an atom is. Atoms are the smallest particles of any given matter. Elements are made up of atoms. We are all made up of atoms. So let's look into what an atom is. After Democritus proposed atoms, people started thinking about how atoms must really exist. And this thought led to the atomic theory, and that's the idea that matter is made up of fundamental particles called atoms. Antoine Lavoisier here concluded upon experimentation that when a chemical reaction occurs, matter is neither created nor destroyed, it's only changed. We just rearrange how it is placed. And this is known as the law of conservation of matter. The law of definite proportions, which we talked about last week as well, was defined by Joseph Proust. And it's the principle that the elements that comprise a compounds are always a certain proportion by mass. So I have mentioned before the example of H2O. In every compound of water, you will have 2 hydrogens and 1 oxygen, no matter where you find water in the universe. Then John Dalton came around and he devised an atomic theory to explain the principles of Proust and Lavoisier. Remember, Lavoisier had the law of conservation of matter. Proust was the law of definite proportions. So Dalton's atomic theory, he said that all matter is made up of atoms. All atoms of an element are identical. Now remember, this was his theory at the time. We have since learned that all atoms of an element are not identical. And we'll talk about that whenever we learn about isotopes. 3, the atoms of different elements have different masses and sizes, which is true. And compounds are made from whole number combinations of atoms. That is the law of definite proportions. And he said chemical reactions is just a rearrangement of atoms, like we have here. We have 4 hydrogens on the left side, 4 hydrogens on the right, 2 oxygens here, and we still have 2 oxygens here. And that's because each of these coefficients, these are called coefficients, they get distributed, like multiply. This says how many there are in that molecule or compound, and the 2 gets distributed to each element in that compound because H2O, but we have 2 H2O. So instead of writing H2O plus H2O, it's just easier to say we have 2 water molecules, and this is how we do it. So chemical reactions, we're just rearranging the atoms to form something new. Now, in natural processes, atoms are not destroyed, but they are actually recycled. And we recycle many, many things. We recycle plastics, we recycle metals, we recycle glass. For example, our newly paved roads actually contain tires and glass. We've just recycled them. Here is an example of the nitrogen cycle in nature. We have atmospheric nitrogen here, and it goes into the ground through nitrogen fixing bacteria living in legume root nodules. It also goes into the ground through nitrogen fixing soil bacteria. And as things decompose, it's released into the soil. And you can see it also gets released back into the atmosphere. It's constantly cycling through. So nature, in and of itself, recycles everything as much as it can. So let's talk about atomic structure. As I stated, some things, as we had more technology, some experiments showed that Dalton's atomic theory wasn't 100% accurate. J.J. Thomson discovered that atoms weren't a solid ball that couldn't be broken up. What he did was he used a cathode ray tube and he applied a magnetic field. So if those particles that is coming out like a beam bends when exposed to a magnet, it shows that those particles have charges. And that's what he noticed. The cathode ray tube used to be found in those old boxy televisions. If you've ever seen one and taken it apart, there's a tube, and you could feel that electric energy coming off of it. But you could take it out, turn it on, put some electricity through it, and have a magnet, and it actually does change. It's quite interesting. So he used that tube and had it as a vacuum with gases pumped out of it, with each end of the tube connected to different electrodes. Now, when those electrodes were charged, you had those rays travel in the tube from the negative electrode, which is the cathode, to the positive electrode, which is the anode. And like I said, he put a magnet close to it and he could see it bend. And so he concluded that cathode rays are made up of invisible, negatively charged particles that he called electrons because they had an electrical charge. Now, the electrons had to have come from the atoms of the negative electrode. So he concluded that atoms weren't indivisible, but they were composed of smaller particles, not just negative, but also positive. Because the atom itself was neutral. And if he knows that there's a negative particle, there has to be a positive particle. Now, the anode also emitted particles, but those particles were positive, and they were deflected by electrical and magnetic fields, but in the opposite direction of the cathode ray particles, which makes sense. If the negative charge is attracted to the positive side of the magnet, the positive charge is going to be repelled by the positive side of the magnet. Thomson showed that these were positively charged particles, known now as protons. Now, the amount of the charge of protons and electrons is equal, but the mass of protons is not equal to the mass of electrons. The mass of a proton is actually similar to the mass of a hydrogen atom, but the mass of an electron is 1,837th that of the mass of a hydrogen atom. So whenever we're looking at an atom and trying to find the mass, we basically say the electron mass is negligible compared to the mass of the proton. Thomson continued to do work, and he actually showed that neon had two different masses, which again affected Dalton's atomic theory about all atoms of the same element being exactly the same. So he discovered isotopes. Now, isotopes are atoms of an element that are chemically alike, but they differ in mass. The protons and electrons couldn't account for the differences in this mass, so there must have been a third particle to do this. This particle is a neutron. A neutron is a subatomic particle that has a mass equal to a proton, but no electrical charge. He took all of this into consideration and tried to determine how these particles were arranged. And he pictured it like a ball of chocolate chip cookie dough. He called it the plum pudding model. So this plum pudding model, he said that you had this ball that was positively charged. And then the electrons are like chocolate chips that are just stuck throughout it. And they're stuck in place. But scientists didn't necessarily think that made sense. Some were on his side, some weren't. And Rutherford decided that he was going to continue testing to see if he could determine what the structure of the atom was. So Rutherford sets up a lead shielded box, and it contains polonium, which is radioactive, and emits a beam of positively charged subatomic particles called alpha particles through a very small hole. And the sheet of gold was surrounded by a screen that glows when it's struck by the positively charged particles. So his experiment looks something like this. Here's polonium inside with the positively charged particles. And there's a slit in the screen so that the particles could go through. And he puts gold foil there. He knows where it should go if it goes straight through the gold foil and it's pure gold, but he noticed that some were being deflected. Most of them are going straight through, but some you notice here actually get deflected. So he said it's not like a ball of chocolate chip cookie dough. And he came up with a new model. And he said, well, most of the particles pass through the foil. If everything's passing through the foil without hitting anything, the atom must be mostly empty space. Because so few particles were deflected, they said that the atoms contained a very dense positively charged core called a nucleus. Because most of it, if I draw it here so you can see, most of it just passed through, right? And these are positively charged particles. But the few particles that actually hit the nucleus, where all the positively charged particles were, deflected. And they bounced back. But most of the particles actually went through. And that's why they said this must be mainly empty space. If it weren't, and the whole thing was positive, like the dough of a cookie, if that whole cookie were positive, we'd have even more deflect than actually happened. So instead, all the positive charges must be in this very dense, compact core in the center of the atom, and the rest is just empty space. So, in fact, atoms are mostly empty space. If you look at a hydrogen atom and you increased hydrogen's proton, it's the simplest atom. If you increase hydrogen's proton to the size of a golf ball, the electron would be about a mile away, which means the atom would have about a 2-mile diameter. And that's huge. And you can see, if you can visualize that, you can see how much empty space an atom really is. Now, in 1 drop of water, there are 6.5 times 10 to the 21st atoms. That tells you just how tiny atoms actually are. So we're mainly empty space. If you could see us at the atomic level, you would see a ton of empty space. But knowing that everything is compact and we're looking at the macro world, the macroscopic world, we can't tell that things are mainly empty space, even though they're solid. It's just atoms are mainly empty space. So let's do some practice. What is the charge of the proton? Remember, pause it, try to do this on your own, and then come back to answer the question. So what's the charge of the proton? It's positive. Remember, protons are positive. So I'm just going to make a positive sign here. What's the charge of a neutron? Take a pause, answer it. Neutron has no charge. It's neutral. And if you can't remember all the charges, neutral, neutron, they both start the same way. Proton and positive both start with a P. So P and P. Like I said, I need little things to remember. Who provided evidence for the electron? Do you remember the scientist who provided evidence of the electron? It was J.J. Thomson. Now, who provided evidence for the nucleus of an atom? This was Rutherford. All right, that's it for today. And if you have questions, let me know. And I'll see you guys next class.